Everyone, and welcome. My name is Jake Valancourt. I'm a co-founder of 10X Engineered Materials, and I'm joined by my colleague and our CEO, Dr. Stephen Ritchie. Today, we're going to be talking about strategies for your operational success, of course, with a focus on how to boost your profitability. And what we've observed as a company is that essentially customers are needing to optimize their blasting system and process, and when they do that, they are a lot more profitable. So Steve's going to be taking us through the nuts and bolts of that today. So without further ado, Steve, take it away.
Well, good afternoon, everybody. Jake said, I'm Steve Ritchie. I'm the CEO. I'm a co-founder with Jake of 10X Engineered Materials. Today's webinar is all about opportunities to be more productive and make more money in blasting. We've been in business for about 5 years now and have had the opportunity to see blasting operations of all shapes and sizes. The thing that strikes us over and over is how much opportunity there is out there for improvement. A lot's being left on the table. Today's discussion will be about why profits are being left on the table from a science and engineering perspective. Like a lot of other things in life and business, breakthroughs are in the details and in understanding why those details are important. Many of you know by now that 10X is a different kind of abrasives manufacturer. We were founded in 2018 by engineers who were developing a repurposing solution for the byproducts of mineral wool manufacturing. Our true north mission that guides all of our decisions is to bring new and innovative ideas and products into the world to help people and the environment. And that's why we're doing this webinar. Our hope is that sharing what we've learned will be a benefit to all of you. And we would love the opportunity to work with you to capitalize on these opportunities. So first, let's take a look at what an ideal blasting operation would look like. First and foremost, the ideal blasting operation is safe. Workers can go home to their families with peace of mind knowing that they work in an environment where they won't get injured or sick. It's a well-oiled machine. Schedule and budget targets are met or exceeded because blasting speed is maximized, abrasives and fuel use are minimized, and most of working shift time is productive. Tasks are done right in the minimum number of process steps and on the first pass. There's rarely a need to do anything twice. The efficiency and profitability of the ideal operation also allows for competitive bidding and the ability to maximize revenue by completing more jobs at higher quality and in less time. We're going to go through 3 areas where we see the most opportunity. And those are equipment sizing, selection, maintenance. The second is blaster training and skill. And the third is management data collection and tracking. So the objective of blasting is to accelerate abrasive particles to a very high speed to perform the work of cleaning and preparing a surface for coating. That high particle speed is an energy state, and that energy is imparted to the surface when the particles collide with it. All of the mechanical energy for blasting is provided by the compressor motor. The compressor raises the pressure of a specified volume of air. The energy of the air is essentially, it's just the pressure multiplied by the volume. So in other words, pressure is mechanical energy of the air per unit volume. So viewing pressure as mechanical energy, thermodynamics says that once the compressor has raised the pressure and the air exits the compressor, the energy can only decrease from there. I mean, ideally, all the energy from the compressor would be used on the surface. The problem is that everything in between, the hoses, the fittings, the bends and turns, the dryer and the pot, all contribute to expending the mechanical energy of the air before it reaches the nozzle. Since energy is pressure times volume, and the volume doesn't change much from the compressor to the nozzle, the energy expenditure through the system shows up as pressure reduction. Everything that resists the flow of the air through the system reduces the pressure and decreases the efficiency of blasting. It's the pressure at the nozzle, not at the compressor, that matters in blasting. And it may seem like paying attention to the details along the way to minimize these losses would offer maybe marginal productivity gains, but that couldn't be further from the truth. Surprisingly huge improvements in productivity and profitability are possible, and most times with little or zero capital investment. As we just said, the compressor is the engine of blasting. It has to have enough capacity in both pressure and air volume to generate a productive pressure at the nozzle. And that's accounting for all the losses along the way and accounting for the number and sizes of the nozzles being used. Undersized compressors is one of the major limitations that we see in both large and small blasting operations. The compressor should be sized for the maximum expected number and size of operating nozzles and the desired maximum pressure at those nozzles. We recommend compressors with a maximum pressure of at least 150 psi to allow for setting the compressor between 140 and 150 and to ensure that pressures well above 100 psi at the nozzle can be achieved when needed, provided the rated CFM is also high enough. You can always set the compressor lower if lower pressures are needed, but you can't set it higher than its maximum when the additional pressure can make all the difference. And next is the maximum flow rate of the compressor, or the CFM. The rated flow rate should take into account all air demands, including the nozzles, breathing air, and any other loads that the compressor needs to supply. There's a volumetric flow rate of air required to achieve a given pressure, say 100 psi, for a given nozzle size. One number 8 nozzle operating at 100 psi requires about 340 CFM. A number 7 at 100 psi requires 255 CFM per nozzle. So a compressor supplying a 4 nozzle pot with 4 number 8 nozzles would need to have a rated flow rate of about 1600 CFM to ensure that at least 100 psi can be achieved at the nozzle. Most rental compressors that we see in shipyards that supply 4 nozzle pots are rated for 1600 CFM. But we also encounter many operations where the compressor capacity is nowhere near high enough to supply the air demands for productive blasting with the number and sizes of nozzles being used. And this is a barrier, but all is not lost because there are many other ways to improve a blasting operation. The air that comes out of the compressor has moisture in it, and that moisture increases in high humidity environments. Moisture separators on compressors and pots, they help, but they can't be counted on to keep water from combining with abrasive, accumulating in the pot, and also reaching the nozzle and the surface that's being blasted. Moisture that reaches the pot and mixes with abrasive can substantially limit the uptime, productivity, and profitability of blasting. Wet abrasive in the pot can cause the abrasive to agglomerate, stop flowing through the metering valve. And there's often downtime to clean the pot and refill with dry abrasive, sometimes repeatedly. The moisture that reaches the nozzle with the abrasive creates a film on the surface that traps abrasive residues that would otherwise have been blown away with dry air. And those residues can cause rapid rust bloom and the need to reblast before coating. Rework is an enormous and unnecessary cost that expands schedules and just kills profitability. The moisture on the surface will evaporate, but the residue will be left behind, and it can decrease the coating quality, the coating performance, and ultimately affect the service life of the asset being blasted. So in other words, air dryers are worth their weight in gold. You want to blast with dry air. We recommend deliquescent air dryers rated for the same volume and pressure as a compressor in field operations. And we find that the refrigerated air dryers that come with central compressors in blast booths work just fine. They work very well. So many of the problems that limit productivity, profitability, and blasting operations occur in the pot assembly. The pot works by splitting the air from the dryer in two ways. A small amount of air flows into the pot to keep it pressurized, and the rest of the air is routed to the bottom of the abrasive metering valve at the bottom of the pot to receive abrasive and be transported through the blast hose to the nozzle. The key in all of this is that the pressure inside the pot on the inlet side of the metering valve is nearly the same as the pressure in the air line that passes underneath the pot at the outlet of the metering valve. Those pressures need to be the same or really close, because metering valves are designed essentially for gravity flow of abrasive. Anything that upsets this balance of pressure on either side of the metering valve can wreak havoc. And as an example, air leaks in the pot through fittings, the ball and port seals, or any other leak will tend to decrease the pressure in the pot above the metering valve on the metering valve's inlet side. So the pressure is lower there. If the pressure is higher in the line below the metering valve than it is in the pot, then the flow of abrasive through the valve will slow down or stop. And blasters correct for this by partially closing the choke valve, which has the effect of decreasing the pressure of the air that goes under the pot and to the nozzle, and that loss in pressure can severely decrease blasting productivity. Using a choke valve to get that pressure balance across the metering valve just right is difficult, if not impossible. It often ends with far too much abrasive being forced from the pot through the valve and into the blast hose, resulting in slower particle speed leaving the nozzle, massive waste of abrasive, excess dust generation, and higher labor, cleanup, and disposal costs. It can also significantly accelerate wear in the metering valve, blast hose, and nozzle. Choke valves are meant to be on-off valves that manually start or stop airflow to the blast hose and nozzle. They should never be used to control abrasive flow or pressure in the blast line. Pressure should be adjusted by changing the pressure setting at the compressor or using a regulator in the line between the dryer and the pot inlet. But a regulator is one more pressure loss in the system, so we prefer adjusting pressure at the compressor. Abrasive flow through the nozzle should be adjusted using the metering valve with a properly sealed pot. Leak checks and repairs should be done regularly, if not daily. A blasting operation with a sealed and properly functioning pot will be far more productive and profitable than one with a leaky and malfunctioning pot. So hoses can gobble up pressure, especially when they're not sized properly. The diameter, inside diameter, and the length of hoses essentially determines what the pressure loss will be for a given airflow and air pressure. There are three types of hoses used in most blasting systems. The connection hoses, or bull hoses, connect the compressor to the air dryer and the air dryer to the pot, and have to be sized for all downstream air demands. If you got 4 nozzles downstream, then the bull hose needs to be able to accommodate the airflow for all 4 nozzles with minimum pressure loss. Hose length, bends, and loops also cause additional pressure loss, so it's best to locate the compressor, dryer, and pot close to one another so that bull hoses are as short as possible. And the same goes for blast hoses. They should be sized for the maximum expected air demand or the largest expected nozzle and the highest desired pressure at that nozzle. A rule of thumb is that the internal diameter of the blast hose should be at least 3 times the diameter of the nozzle orifice. So for a number 7 nozzle with a 7/16 inch orifice opening, the hose should be about 21/16 or about 1 1/4 inches. But if the runs are longer, if the blast hose runs are longer than about 50 feet, then we recommend sizing the hose up. So in the example of the number 7 nozzle, we'd say go ahead and use a 1.5 inch hose for the longer run to make sure that the hose doesn't cause excessive pressure loss. When in doubt in hoses, go one size up. There is just no sense in risking such an easily avoidable loss in pressure and productivity. Whip hoses are just smaller diameter hoses often installed in the last section of a blast hose before the nozzle to increase maneuverability for the blaster. And they also help match up the internal diameter of the hose with the inlet opening of the nozzle, and that decreases wear on the upstream end of the nozzle. But beware of whips. Whips can eat a lot of pressure because they are not sized for the total flow of air to the nozzle. We recommend keeping whip lengths to about 10 feet and no smaller than 1 inch internal diameter. Most nozzles on the market work just fine to accomplish the objectives of blasting. Standard Venturi nozzles provide a nice balance of particle speed for cutting and particle spread for a nice wide blast pattern. Longer nozzles like the XL prioritize speed over spread and are very effective on thicker, more difficult coatings where cutting speed is most important. Nozzle sizing and the selection of nozzle size is driven by the size and substrate that you're blasting and the capacity of the compressor. And we often see blasting operations that are using nozzles that are either too large for the given capacity of the compressor or so worn out that the orifice opening is 1 or even 2 sizes larger than it's supposed to be. Generally, we recommend using the smallest nozzle necessary for efficient blasting because this minimizes fuel, air, and abrasive usage. However, larger nozzles are way more productive on large surfaces like chip hulls and tanks. In those cases, we recommend the largest nozzle that the compressor can handle and to keep the pressure at the nozzles above 100 psi. We actually prefer 110 psi at the nozzle for our abrasives. And the nozzles should be gauged weekly at a minimum and replaced if the orifice is a 1/16 inch larger than its original size. So now we're going to talk about the blasters. Blasting is a tough job. I have great respect for blasters. It's complex. It's done in God-forsaken places. It's exhausting. And it takes serious attention to detail to accomplish the specs of a job. And we're often surprised to see nearly identically designed blasting systems where one of them far outperforms the other. In many of these cases, it's the skill of the blasters that accounts for the difference. Now, it wouldn't be fair to say that blasting companies are not aware of the importance of training blasters, but I think it might be fair to say that the potential impacts on productivity and profitability are underestimated. A skilled blaster can accomplish the same task as an unskilled blaster in half the time, better in many cases. The blaster in the photo on the slide is the best I have ever seen. This whole crew blasts with number 10 nozzles at between 105 and 115 PSI at the nozzle all day, every day. They know how to do it without getting tired. They use their body weight to support the nozzle and move the nozzle with their shoulders as fast as the abrasive will allow them to go on a given coating. These guys understand the interplay between pressure, abrasive metering, and nozzle distance and angle with the surface. For example, when a particular area is difficult, they'll move in. They'll move the nozzle in closer. When it's easier, they move away for a bigger blast pattern and more coverage. They also know how to blast to the paint spec. They don't waste their time getting an SP10 finish if the spec calls for an SP6. I mean, they go faster. And they move their feet quickly from one area to get to the next area with little wasted time. They hustle. There is so much to blasting, and there's such a high return on detailed training and mentorship. Blasters want to be good at their job. And when they get good, they can accomplish more for their business than probably everything else we've discussed in this presentation so far. The gains from blaster skill can literally be shockingly high. This slide is about not flying blind. Most blasting operations don't know where they are on the spectrum of productivity and don't have the information and data they need to identify problems or to continuously improve. You just can't improve what you don't measure. And measurement drives worker behavior. Most workers want to perform well in their jobs, but don't have a quantitative goal. Much of what we have talked about can be measured and tracked. It's extremely important to know the idle pressure at the compressor or where the compressor is set, and the pressures under full load with all nozzles turned on at the compressor, the pot, and the nozzle. The pressures at the pot and nozzle can be easily measured by inserting a needle gauge into the blast hose near the pot to get the pot pressure or close approximation, and in the blast hose near the nozzle to get the pressure that's actually at the nozzle, your working pressure. It's also paramount importance to record all pot refills to track abrasive usage over the course of a job. If nozzle timers are used, which we love to see, then the operation will know how efficiently time is being used and can correlate pot refills with nozzle time to calculate abrasive flow rate through the metering valve from the pots. And productive output, whether that's rail cars or square feet on the hull of a ship, should also be tracked per nozzle on a daily basis. When pressures, abrasive usage, nozzle time, and productive output are measured on a daily basis, the economic performance of the operation is much more clear and problems are easily identified and solved. So, like a lot of things in life, this continuous improvement we've been talking about in blasting, it comes from consistent attention to and correction of what may seem like little things, but they add up to more than we might have imagined. To illustrate this, we created a basic financial model of a blasting operation that accounts for revenue, in this case at a bid price of $3.50 per square foot, and the costs of the abrasive, labor, compressor fuel, cleanup, and disposal. So the profit in this model is just the revenue less the sum of those costs. We'll assume a base case where 8 blasters are doing a 50,000 square foot job with 90 PSI at the nozzle and 100 square foot per hour blasting speed. These numbers correspond pretty well to a lot of large tank jobs, tank liners, and the base profit margin here is 31.5%. So for case one, let's assume that the compressor is set 5 psi higher, and some hoses were right sized to accomplish a total of 10 more psi of pressure at the nozzle. With the additional pressure, the metering valve could be turned down 10%. So you got 10% less abrasive flow. Just that increases the profit by 36%. Now, for case two, we'll assume that the system changes were made to increase the pressure an additional 10 psi, and the abrasive feed could be turned down another 10% by fixing some leaks in the pot, stopping the use of choke valves, or other measures. Now, profits are 65% higher compared to the base case. In case three, we'll assume we did some blaster training and increased the speed, the blasting speed, another 10%. All other conditions are the same. And now we're at 110 psi at the nozzle, blasting 130 square feet an hour compared to the base case, and the profit is nearly doubled. What was bid to be a $55,000 profit job is now $103,000 profit. And what isn't shown here is that this case three achieved a 30% reduction in schedule. It went from 11.7 shifts to 8.3 shifts. So case four assumes that this is a continuous operation, and those 3 whatever shifts are now used on the next job to earn additional revenue. So if you take that into account, the profit in dollars is 3 times the base case, and the margin is 125% higher. And honestly, there's nothing about these cases that's unrealistic. In fact, more than this is possible. Blaster training alone can accomplish case three. System improvements, training, data tracking together can literally be game-changing. So there's a lot more possible out there than what we certainly thought. We had a lot to learn when we started this business. We didn't know what we didn't know when we first started. But in trying to help our customers get the best possible results, we had to learn it. And what we learned is that you need to do these things. And if you do these things, magic can happen. So that's the end of the presentation. We greatly appreciate everyone attending today, and we hope this will give you ideas on how to improve your or your customers' operations. We're going to have a Q&A session, and I'll turn it back over to Jake.
Hey, Steve, that was great. And we've got quite a few questions rolling in here, so we're going to go into the question and answer. So Steve, the first question that we got is actually asking, what is the meaning of decreasing feed rate, and how can you do that? So could you talk about abrasive feed rate and just go into that question before we go to the next?
Yes, what I mean by abrasive feed rate is the flow of abrasive through the metering valve at the bottom of the pot. Feed rate would be measured in, say, pounds per minute or tons per hour. It is the amount of abrasive flowing into the blast hose from the pot. I hope that clears it up.
Yeah, I think that did. Thank you. And we've also been asked, what is the best way to manage data collection and tracking proficiency for different projects with different specifications?
That's an excellent question. that would be something we'd, if we were involved, we would sit down and talk about. the spec drives a lot. And what we see, as I told in the example I showed you, that the best blast crew that I've seen, they blast to the spec. There are times they were going way faster than they were on another job, and I asked what's the difference, and they said this job only requires an SP6. So how much faster can you go to get an SP6 as opposed to an SP10 is hard to know. I think generally that you track the same data and see, and just compare to the other jobs, communicate with your workers, look at the surface, inspect the surface, and make sure you're meeting the spec. And if you're exceeding the spec by too much, then maybe the blasters can go faster.
Yeah, and I think I'll remind everyone, we did hand out 3 different documents. Two of them are actually the same. One is a PDF version, one an Excel version. And these are examples of what you should be doing as a daily and a weekly checklist so that the system doesn't fall out of an optimized state, essentially. These are the things that we would look for if we're on your blast site. And our field engineers are looking at this regularly when they're on a blasting site. And then we also included essentially a data collection template. It's just an example. There are ones that are much more comprehensive, but we wanted to show you what we felt like were the minimum points that you should be recording on a regular basis so that you can understand how you're progressing along with your blasting operations. So we have a couple other questions.
So can I comment on that, Jake?
Yeah, sure.
For our purposes, when we're going in and trying to help a new customer, say, and we want to measure their performance with our abrasive, because we want to make sure that they're getting all the value from the abrasive. And when we collect that data and we can get most of that data, we almost can see immediately what the opportunities for improvement are in that operation. That's the power of it. The power of it is you'll see if there's a problem in the data. Just because something's awry, something that's supposed to be one thing isn't, and then you do a little bit of troubleshooting, you fix it, and you're back to productive blasting. That's the power.
Yeah, the data is really important, right? It's what helps us understand where to focus next. What's the next best thing that we can do to increase the performance? I have another question. We have a few more questions, but one of them is what we used for the cost of compressed air. And I think that we most likely are using a range. It's going to vary depending on the cost of electricity or diesel, and also where in the world you are. We have some customers overseas that have a different cost basis than we do in the U.S. So if you could just talk a little bit about that, and then I'll get on to the next question set.
Yeah, I made some assumptions. I'll tell you what those assumptions were. I assumed that what I call the equipment use cost is $25 an hour. Burden labor was $30 an hour. I assumed the landed abrasive cost, the cost of the abrasive at 20 cents a pound, a cleanup cost of $50 a ton, and a disposal cost of $30 a ton. That's what I assumed for that simple financial model.
Okay. Yeah, and I know some of those numbers are conservative, and I think that's some of the feedback we're getting. Yeah, it's going to depend on where in the world you are. Labor costs, energy costs, right. All of these things are.
I didn't want to overestimate those costs. I wanted, if anything, to
Yeah. What I can say is, we've seen both our customers and folks who are not our customers yet follow our guidance that was given here, and the results are similar. If you think of it in layers, like you're adding things that you're essentially managing in the blasting process, your performance, your profitability, and the speed at which you will get the work done, and the quality of the work will all improve over time. Um, and we've seen that sort of across the board. So this is
And the interesting thing, Jake, just to add to that, is it doesn't happen in one day.
right. Yeah.
There's a process. It takes a little time.
Yep.
I would say weeks, sometimes months, but it takes a little time to get through and correct for the problems.
Yeah. I don't.
But the other things that's surprising is that it's often not a huge capital expenditure.
Yeah, that was one of the next questions. How much capital needs to go in to get these types of improvements in a typical blasting setup? And I don't know how you'd characterize a typical blasting setup, but that's one of our questions.
A lot of times it's the cost of some hoses, the cost of a new metering valve, the cost to fix leaks. So much can be accomplished with those little things. The idea of having to get a larger compressor, right? That's a bigger deal. Compressors are expensive. However, if you look at the numbers that a right-sized compressor can offer you in terms of return on profitability, heck, just that fictitious job that I showed, that little financial model, there was enough money in there to buy a compressor just on that job, on the additional profit. So the return, if you have to invest capital, which really hasn't happened, it's rare that's happened. But even if it is necessary, it's worth the investment. Yeah. It'll pay for itself.
And we've had customer cases too where that's what we think is necessary, and instead of writing a big check, they go out and they rent the equipment that's in the condition, or even potentially better condition if they're looking at used equipment, and they run a job or two under those conditions, and then they see the benefit, and they always invest after that. So there are other ways to measure the impact, right? If you're doing the data measurement that we're suggesting, you're measuring these metrics, and you have that insight, you can start to improve right away, even if you didn't go up to that level where you need to make investment. But most cases, we don't see that. We have another question here asking about wet blasting, and then a question about how much additional air should you need. If we have a CFM chart, I'll post the link to the CFM chart and a resource on our website that goes into that. But could you talk a little bit about wet blasting, and if this would what we're suggesting would carry over into that arena as well?
It does. The metering of the abrasive in a vapor blaster is as important as metering the vapor in an air blasting system. It's a little different, and it depends on how the vapor blast machine operates. There's a pump on some vapor blasters that pressurizes water and abrasive in the pot, and then you have your air compressor. Well, the abrasive is metered in an entirely different way. It's metered on the pressure difference between the water and abrasive in the pot and the blast line. And so the abrasive is fed to the blast line from water pressure. It would be a slightly different conversation, I think, if we were going to go through this for vapor blasting. But I would say that we covered air blasting today because it's by far the most common, most applicable for the widest audience. But I think vapor blasting is going to grow. It has a lot of advantages. One of them is the low dust during blasting, the exposure. It has a number of advantages, but it's probably not a very satisfying answer to the question. It is different. Vapor blasting is different.
Another question that we're getting is along the lines of using the product. Sorry, not the product, but using this process system wide. How does it compare and contrast in the system where you have manual labor blasters who are doing the work versus most of the physical blasting work being done in robotics? Do these metrics still apply, or would you be measuring different things? I think that's what this person is trying to get to.
No, I think it's very similar. The only thing is that the robot is perfectly skilled, nearly, and doesn't get tired. You can more easily raise the pressure. A lot of blasters don't like raising the pressure because they get exhausted, and I don't blame them. But there's a way to learn how to support the nozzle at high pressure and not get tired. It is tough in enclosed spaces or in tight spaces where some of these blasters have to work. It's very difficult. But no, I think everything, just about everything but blaster training applies to an operation that's using a robot.
Okay. We had one more question, which was just about the webinar itself. Is the presentation available to download or view later? And I typed in the chat, but yes, everyone who registered will get an email within a day or less of a recording, and that recording should work for 2 weeks. And then 10X will make it available on our YouTube channel later in the month of November. So Steve, if you have any final remarks, please feel free to wrap it up, and then we will close this up and send folks to the survey where, we'd love to do something like this again and just look for everybody's feedback on what they thought of the webinar and what they'd like to see covered next.
I would just say that we would love to work with you guys if you would like for us to help you accomplish this. Give us a call. We would love to go through this with you.
All right. Well, thanks everybody for attending. We appreciate it. Have a great Tuesday. Be safe, and reach out if you have any further questions. Bye, everybody.
Thanks, everybody.